Hi, this is David Leigh Hudson from Siemens. I am our business development executive responsible for our Fibersim portfolio. With me, I have Kurt Politowicz. Kurt, would you introduce yourself?
Yes, my name is Kurt Politowicz, and I am a pre-sales consultant for Siemens.
So today, we're going to go through a little bit of an overview of Fibersim using a specific cowling part. We'll do an introduction. We'll go through a little bit of what's a unique design methodology in the industry called Multi-Ply. We'll go through a demo roadmap that Kurt will introduce so that we make sure that everybody understands and can follow along. We're going to do an interactive demonstration and then recap with the Fibersim benefits. Kurt, you want to speak into anything else on this particular slide?
Yes, I'd like to explain one thing. So this part actually is a multi-laminate design. It has an OML laminate with some plies, film adhesive, and core. Then we used Fibersim to generate an overcore laminate, on top of which we've generated a new multi-ply design. However, we're not going to be covering that upper laminate today. I just want to explain to you that the part has two laminates and that Fibersim has a tool to generate overcore as well as IML surfaces. Thank you, Leigh.
Thanks, Kurt. So, what is Fibersim and why do customers actually purchase Fibersim in the first place? And what is the value that it provides to our customers? And so here are some of the challenges that we see in the industry, right, where we have inefficient data flow. They don't necessarily have a digital twin for composites. It really creates a challenge in the transition from if you're doing analysis, transitioning into detailed design, and then transitioning into manufacturing. Often there are disparate solutions, and it really makes it hard to capture and utilize or reuse the information for that composite part in the right context at the right time for that particular discipline. Other things that really are challenging for customers that don't necessarily have a level of automation is understanding the behavior of the material in the context of the shape and the manufacturing process that's going to be implemented in producing that part in the first place. Something that we can actually do in that particular digital twin itself. Kurt will actually demonstrate some of that today. And then, what we see a lot of is that's costly and time-consuming design being done on the manufacturing floor, especially with respect to design for manufacturing. Often, customers will understand what needs to get laid up in terms of the laminate schedule of material, but not how to actually achieve that. And so, you'll see a lot of design for manufacturing and then digitalization of data in order to generate the manufacturing deliverables. And again, sort of what I consider, at least in this day and age, a backwards step in the process in order to then produce that particular part. And lastly, sort of this lack of common methods for someone who's a layup technician that end up resulting in and impacting the rate and the quality of those parts. And we've seen customers that actually, a layup tech on shift one will end up laying up the part one way, and it's different than the person that actually lays it up on in shift three. And so, there's inconsistencies in that particular part. The next slide here is actually one to speak about the impact it has from a profitability and a business impact when customers, on the experience curve, manufacturing companies that are deploying limited and very limited, when I say limited, I mean limited design and manufacturing automation, whether that be a design tool for being able to understand what you're going to manufacture and how you're going to manufacture it early on in the process, being able to generate manufacturing deliverables from that and reuse that data, or whether it actually means just using a laser projection or a cutting machine in order to generate or produce that particular part. Those companies that actually implement or deploy limited automation in that production of composite parts, end up having several iterations that are required in order to profitably produce a manufactured design. This second line here is really the companies that end up seeking process improvement by incorporating point automation, again, laser projection systems or cutting machines or even simplistic flattening software. And those investments I'm not saying they're not wise. I'm saying they only incrementally improve the development process and the manufacturing of that particular part. And those companies, really end up becoming incrementally more efficient. And the problem with that is, and the reason for that is because they really start at the same point, right? They start at the same point from a design perspective or from an authoring perspective and design for manufacturing perspective. This last curve here is what Siemens offers, and we offer a different approach. We allow for the creation of a complete digital twin of the composite design. And the value of that is that the data flow actually becomes more efficient and more accurate across multiple disciplines. Let me give you a quick example. So from a design for manufacturing perspective, that design for manufacturing can be done in that digital twin in the early stages and not on the shop floor. And we can actually create the deliverables. It's not like I've got to go out to the shop floor, figure out how to lay this part up, do the design for manufacturing on the shop floor, generate the flat pattern, and then digitize them and optimize them, right? It's something that actually is sort of, it ends up, and I hate using this term because it's not the best term, but ends up being a product of actually that solution in that digital twin being able to capture the three aspects that are going to impact the generation of that part or the production of that part, which is the shape of that particular part, the material form that you're going to use, and the manufacturing process. So those things actually create an opportunity for increased rate, quality, and profitability. At this point, I'm going to hand the presentation over to Kurt.
Thank you, Leigh. So what I'd like to do is give you a quick overview of how the Fibersim solution is used, as Leigh mentioned, across disciplines. So typically someone starts off by developing a loft. And one thing I'd like to point out at this time as well is that Fibersim works on the Siemens NX platform, TV5, or on Creo. And once you have that loft surface, whether you extract that from a solid or you loft an actual surface, we can then go ahead and start to define composite objects on there. And we'll show you this multi-ply technique today, whereby we can help you to very quickly author the design in Fibersim, then assess the manufacturability of that design. The upper middle image shows a ply that has been simulated. After we've actually developed manufacturable plies, we can go ahead and create flat patterns from that. And then as I mentioned in this example, we use the underlying ply definition defined on the OML to generate a overpore surface. So this represents the topology after the plies, film adhesive, and core went down. We make a new surface in Fibersim, then we define film adhesive here and the remaining plies. So as Leigh mentioned, this is a very effective way to help you to speed up the process and make you more profitable, because you can conceptualize, you can change things very quickly. One of the things we definitely want to make sure is that you meet your performance goals. And the process we're going to show you today is specification driven. So it eliminates a lot of the chances for errors in someone not understanding or creating an ambiguous design. Improved communication with manufacturing obviously is going to help with rate. And one of the big things is you want to try and mitigate risks. You don't want to find surprises when you hit the manufacturing floor. I've had a number of customers tell me that parts shouldn't have made process. They should stamp them from titanium because they can't meet splicing specs that the OEM requires or things like that. So it's very important to understand and kind of make more informed decisions based upon the materials you're using, the shape you're using, and not have surprises when you get to the manufacturing stage. So for this demonstration in the next 45 minutes, what I'd like to do is show you how to take this surface model and alter that definition. So we're going to open an X, and I'm going to show you how the different composite objects are created, such that I can alter the design for the OML laminate. After that, I'm going to return to the PowerPoint, show you a few more slides, and talk about how we validate that design. and how we create some of the manufacturing data. Once again, I'll go into the product, come back, and then we're going to talk about some of the manufacturing deliverables. So one of the things that's very powerful is that the same 3D digital twin definition that we create is used to create all the manufacturing downstream outputs, place projection data, the flat patterns, the engineering drawings, the manufacturing plybook instructions. If a change needs to be made, it's changed in one place at that 3D definition, and then it propagates. So you don't have people with information that may be out of sync. You don't have to go and type values into a table you made or build a cross-section by hand. All of it is linked and driven from 3D in a very efficient manner. And today we're going to introduce Multi-Ply, and this technology is a very efficient way to help you author that design rather than using a ply-based approach where you build each curve, link it to a ply object. This can allow us to define specifications and then drive the generation of all the geometry that's necessary. Just a quick overview of what Multi-Ply looks like. We're going to create some overlay zones. And here you can see different shaded colored areas. I'm going to go into more detail about what that is. We have different parts of the tool surface that have different laminate specifications, meaning they have different materials of different orientations, may have core, different numbers of plies, and that's going to be used by Fibersim. So the only geometry requirement is to build this geometry to define the zones. And then Fibersim is going to generate all the engineering layers as well as all the ply layers, ply boundaries based upon that. So if I have an area of thicker to thinner, it's going to build the number of transitions necessary to transition between those two different areas automatically. If I go back and change the specification at the zone level, it will remove those layers when I run the zone layer function again. So everything is going to stay linked and associative. And then once I have this definition for the laminate described, as I mentioned, we can generate a final part surface or solid, or in this case, we generated a overcore surface. So we can then go ahead and build subsequent plies that are placed down over top of the core. So I wanted to take a few seconds to describe this before we go into the product. So here we can see a large purple colored area, violet color. This is what I would consider a full body coverage. And for this example, our design is going to have 3 full body plies. So we create an overlay zone which has just that defined on it. Next, I define 2 more zones which each have core and film adhesive. So we have 2 more pieces of material dropped on top of those previous full body plies. So the area you see that's purple now still has only 3, but in these 2 areas we have 5 components where you see the brown. And then finally we have another reinforcing area where we drop another 3 plies right on top of the existing laminate. So in that red area, we're now going to have a total ply thickness of 6 plies. As I mentioned, Fibersim will build the transitions from the 6 ply to 3 ply area automatically, and then allow us to adjust the spacing between them as necessary. One of the things that we're always praised about is that Fibersim allows engineers to work the way they think. As I mentioned, we're going to have a combination of specifications, what we call laminate specs and material specs, where you will describe what is going to be going in the different areas on the part. Then you'll link that to different geometry on the part when we go and design the laminate. We're going to set the laminate, define the overlay zones. We'll run a function called zone to layer, and that will create layers of material coverage. An engineering layer can be thought of as the full coverage or acreage covered by a ply. It may not be something to manufacture. In the case of a wing skin, you may have a 45-degree coverage for a full area. You may have to splice that into 6 or 8 pieces to make it. So the engineering layer would be that full coverage of a given orientation. And then the plies, the manufacturing plies themselves, are going to be the individual pieces that go into the tool surface. So we'll derive the manufacturing definition from that engineering definition. As I said before, any change to the driving specifications, any change to the zone information, overlay zones, will propagate all the way through to the manufacturing outputs. So here's a very quick way of pointing out this process of the methodology. We define the laminate or layup surface in Fibersim. We then define the rosette, which orients the material for positioning the different orientations of material on the tool surface. And then we define the overlay zones, which you've seen shaded previously. So these are basically a few boundaries on the surface. And then go ahead and define a laminate spec to associate material to a given zone. So in this case, you can see the red color is assigned for this OML belt area. In that area, in the upper left-hand corner, is going to receive 3 plies, 0.57 millimeters thick, and it's 3 different plies of orientation 0, 45, and 0. After we've defined these overlay zones and laminate specs, we have to create two more things. We create a offset spec, which tells Fibersim how far to space the curves, if in fact it has to make some. If we have neighboring areas of different thickness, Fibersim is going to go ahead and create transitions for us at 6.35 millimeter spacing. And then we create a stagger profile, which describes what we'd like that cross-sectional behavior to be. You can change this at any time. When we originate a design, we typically leave it set to linear ascending. Here are some standard types that are available out of the box in Fibersim. You can also make any custom transition by dragging and dropping the curves in a visual editor for each transition. After you've run zone to layer, Fibersim automatically makes these transitions, and then it makes the resulting layers for you. So in the next few minutes, we're going to pop into the product, and I'm going to show you what these geometry requirements are to author this cowl laminate. We'll review the laminate rosette. I'll show you the overlay zones and the laminate specs. I'll then show you how zone to layer analysis is performed. That is going to create transitions, and I'll just show you the transitions and how they can be adjusted. And that automatically creates the layers. I'll display the layers that we've made. Finally, I'll discuss how plies are created from layers. So with that, I'm going to go ahead and tab over to NX. And here we can see the cowl surface that was in the illustrations there. So I need to go ahead and start Fibersim. My icon's covered up, so we're going to go ahead and get it this way. And another thing I'd like to mention at this time is Fibersim is fully integrated in the CAD system. Everything we enter into the Fibersim UI is stored inside of that respective part file. So the part file I've opened here in NX is going to maintain the definition and the links to the geometry. And anytime you share that part with someone else, they have Fibersim, they can open it, they can then use a Fibersim product to make edits and changes. So here we see the laminate as described before. It's basically a surface with two boundaries. So I have a EOP and a manufacturing boundary. Okay. Next, we have to define a rosette. The rosette was defined centrally in the part here. You can see the vector with the little arrow on it that's pointing in the 0 direction. And this is going to help us to properly orient the material as it goes in the tool. After this, I create my different zones. And as I mentioned, I have a full coverage zone, which is basically just using the net boundary from the laminate. It reuses that just like a ply-based definition would. If I edit this, we can see what is comprised here on the overlay zone form. So I have a link to the laminate. I have the rosette definition. I have origin point. I just reusing, in this case, the rosette origin and the laminate from the boundary, the laminate boundary. And I link it to a laminate spec. That laminate spec for this particular area has 3 plies, a 45, a 0, and a 45, each of a specific pre-peg material here. If I click on this, this will show us the familiar Fibersim database that's been used with Fibersim for a long time. It's an XML database, which you can add materials to at any time. And then simply by clicking on its buttons, all the different information about the cost and weight, the thickness, mechanical properties are all associated to that ply object. So you don't have to type in the thickness or the width at any time. Everything is associated directly from this database. So now we have this laminate spec linked to that. We now understand what the specifications are to create the layers for this. Same thing was done to create the core area. So the core area has a laminate spec which has film adhesive and core described in it. So I picked the 2 boundaries, linked them to the laminate spec. And then finally, this belt area, which you saw the laminate spec for previously, has 3 different strips of varying orientation material linked to that boundary. Once that's been defined, I simply come down to offset spec, and I have to create a default offset spec. And here I set it to be 6.35 millimeters. And I asked Fibersim to leave 1 curve at the base location of the boundary, and then 1 curve at each transition area. Fibersim is extremely powerful. You can have triple linear offsets if you'd like. So you can construct actual parametric or parabolic transitions. You can have different numbers of curves dropping at each location. You can do by percentage or by curve count, and they can each have different spacings. So it's extremely powerful in the way that it constructs these transitions to build the various layers that you might want to define. With this defined, I can now go ahead and access the zone to layer function. So if I click on zone to layer analysis, this is going to bring up a form for me and allow me to run the zone to layer process. And what this will do, as I mentioned, is generate transitions and vertices if I have transitions colliding into each other, and it'll make all the different layers for me. So after having done that, we now have a variety of transitions. So I have one right here that you can see where I have 3 different curves. So this is the area with 6-ply stick. So Fibersim understands that 6 to 3, and it automatically makes those 3 curves for us. This part is not that busy as far as the number of transitions we had to make. We have one around both of the core areas because the film adhesive can get dropped off by 1/4 of an inch or 6.35 millimeters away from the boundary of the core. Okay. This also constructed all the different layers. So here, if I tab down through the list, I have my first full body 45. I have a reinforcing 0 degree. I have a full body 0, 45, full body, and then I have my 2 film adhesive layers. At the same time, Fibersim constructed core layers as well. So it made 2 core layers for me automatically based upon that laminate spec definition. And inside there, we have the core thickness specified as 3.17 millimeters. So now we have basically completed design for this part for the OML. Okay. To create plies, we're simply going to create plies based upon these layers. It's a very simple process. You click on the ply object, the layer object, click generate plies, and then Fibersim creates a ply object, which is the exact same shape as the layer object. And then in the next section, we're going to look at how we deal with that and how we splice and do different things to make it manufacturable. So with that, I'm going to return to the presentation. And so what I've just shown you is how we can enable a very concise definition for that composite design. Fibersim creates all the different boundaries for the layers and plies that are required. And this does definitely help alleviate any of the errors associated with manually typing in offsets for values for splices or for doing any kind of other geometry creation. One thing to point out is that those glowing curves that you see here on the image on the left, these are virtual curves that Fibersim manages. We're not building a lot of geometry in the background, so the model isn't getting appreciably heavy. I've seen some designs from other tools that you have to create a bunch of closed curves for every ply boundary, and the models get very heavy weight. This is very easy. It makes it very easy to make changes too. We can adjust the boundaries and make the new drop-off curves without having to erase geometry or fit geometry. At any time you'd like to create geometry, we have a capability to do that. You can make persistent curves, but it's not a requirement to use Fibersim and to make all the manufacturing data. The next thing we're going to do is look at how we validate the design we created. Here you can see one ply that's already been spliced, and you can see that it's manufacturable. What happens when we go to run the simulation, as Leigh mentioned, Fibersim will look at the geometric shape. It's going to evaluate the material form that we selected from the database, whether it's woven, unidirectional, tow, whatever it might be, and the manufacturing process we specify, whether it's a manual hand layup process, whether it's tape laying or fiber placement. And then Fibersim is going to display for us what the deformation challenges are in that ply. So in this particular full body 0 degree ply, you can see we have quite a bit of issues going around this heavily curved area. There's a little bit of trough here, and there's a curved area that's kind of converging. This causes the material to bridge and actually will tear in this area, I believe, if you try to lay this up. So Fibersim brings this immediately to your attention. We have also a variety of simulation techniques, even for hand layup, that I'd like to point out. So this is what we call our standard simulation. This looks like a pebble in the pond when you drop that in there. So it's like somebody's laid the material down and working it out in concentric rings. We also have the ability to smooth along a curve or at a bias orientation. So when I show you the plies that go here for the 45, I can actually smooth it along the long axis part here, even though it's a 45 degree material. And that will be communicated not only from the design in Fibersim, we maintain the fiber rotation strategy, we communicate that with the analysis group, as well as onto manufacturing. You'll see these images on the ply book when we show the manufacturing illustrations. So one of the things that's very powerful about Fibersim is its ability to identify material width concerns. So the materials database we have, you enter the roll width of the material as it's going to be purchased. When you run the simulation, Fibersim will tell you the material was exceeded and alert you to the fact you can't make that part, that the material is not large enough. It then will allow you to create curves on the surface and to create automated splice curves for that. So this part actually is so small, it fits with the material width. It didn't require that we do any type of splicing in that regard. So when I go into the product in just a second, I'm going to go ahead and create a little dummy laminate and show you how splice groups work, because it's very, very powerful. And once again, all of this is parametrically driven. If you want to change the spacing, you can change the spacing very quickly, and it updates. You're not building curves and erasing curves. You don't have to keep track of where the last transition was, or make sure you don't splice on top of another curve. Fibersim will basically step over at the values you give it, and it'll create overlaps or butt splices for us automatically. We also have the ability to create slit darts and V darts by simply indicating points on the surface. After we've run the simulation, made accurate fiber path results, we know that we can make the plies as designed. Then we go ahead and generate the flat patterns. This is done at a push of a button automatically. Here you can see the flat patterns for the OML have been laid out. The flat pattern is going to include any of the excess for the MEOP. If you run the extended producibility, it's going to have the change in shape of the flat pattern based on darts and splices. And it's going to account for all the material draping effects. And you'll see that in a moment when I go back and look at some of the plies simulation results. One thing I also like to point out is a very powerful associativity between, so Fibersim ply object acts like a link between the 3D definition. So here when I click on the ply object Fibersim, I see the boundary illuminated as well as the simulation results, and this corresponding flat pattern associated that lights up. So if you're doing a design review or something, it's very easy to walk through and have a discussion with somebody who might be doing manufacturing planning and understand what's entailed in laying up the part. So in the next few minutes, when I pop back over into the product, I'm going to highlight Producer results for supplies and evaluate the fiber paths. I'm going to review the material width warning, as I mentioned, on a dummy laminate, so that I can show you how to generate a material width curve and how to generate a splice group, even though it wasn't required for this design. And then after I do that, I'll go ahead and highlight all the splice plies that I made for this design. We'll look at the simulation results for each of the plies that I spliced, and then later you'll see the flat patterns that are associated with those. And then we also have a video later in the deliverables section where personnel at SDA went ahead and laid up the plies that I actually generated in Fibersim, so you can see the exact ply shapes and where the simulations showed there were issues, where they had to do a little bit of work when they're smoothing the plies onto the tool. Okay, so now we're back in Fibersim, and what I'd like to do, this first step here, is to go ahead and toggle to that other laminate that I mentioned. So I'm going to go to my demo laminate, and on this demo laminate, I have a series of 5 layers created. They're all 45-degree layers. What I'd like to do first is I'd like to take this layer 1 and generate a ply from that. So when I do that, I now have a ply object created, and I can now run the simulation for this. So I'm just going to go ahead and run the net simulation. So when I run this, I actually put a material override in so that the material would show up as being too narrow. And now if I go to look at this on the manufacturing tab, we can see that my material width has been exceeded, and Fibersim is always persistent until you actually splice the ply. And if I'd like to preview where that material width line is, I can click this preview button. And so from this corner to this edge is the width of 685 millimeters. Okay? I can move that material width preview curve to any location I'd like. I'm going to go ahead and just move this by 65 millimeters. So I've got it lined up about where I had it when I spliced the actual part for real. And so now I can actually generate a material width curve here. So if I click generate, this will now build a curve on the surface for me in the CAD system. And if I let go of the ply in Fibersim, you can now see that object. Okay? I've not spliced the plies yet, I've just made a curve. Now I could physically splice this using ply-based technology and just grab the curve, tell Fibersim splice it, and it would splice that one ply into 2 pieces. What I'd like to show you is the splice group capability. So a splice group, I've created one here that says for 45-degree rotation. I'm going to link to this curve, which I just created. And now I'm going to review a few other things on the form here. I basically, after linking to that curve, it's showing me what the the propagation of the curve splices are going to be. So I basically set this up so I have a offset spec, and my offset spec is going to be 1 inch. So I'm going to tell Fibersim after it splices to move out 1 inch from that original location, because I want to space my splices away from each other. And then I told it to overlap by 1/2 inch for 12.7 millimeters. This is all I have to do to set up these 2 little items here. And now I can go ahead and apply that splice group to all of my layers. So if I go back to my layers that I previously defined, I can modify all of these simultaneously. I can link it to that splice group, and then I can request that Fibersim splice these plies. And so what this will do is we'll make each one of those individual layers, those 5 layers, into 2 plies each. And so if we return to the ply list here, we can see we have ply 1A and B. They have a overlap of 1/2 inch. Now when I go to the second one, it's going to space out 1 inch, overlap by 1/2 inch, space out by 1 inch, overlap by 1/2 inch. So it's very, very powerful how this is completed. And then I can run the simulation for all of these very quickly. And I'll just show you the last 2 and how they look. The powerful thing about this is that when you're using this tool, this is going to allow you to very quickly splice your plies. I can delete all of these plies at any time, and I can apply a different splice group. I'd like to change the splice group definition. If someone changes the original definition and adds more material to the laminate specs, so it creates more layers, you'd simply go ahead and delete the plies you had and resplice those. It's extremely effective and capable way of doing that. Saves up a lot of time building curves, creating curves, and having to manually keep track of which curve you used the last time. The next thing I'd like to do is I'd like to go ahead and walk you through what I did for the design itself. So the one ply you saw in the PowerPoint had that severe problem up here with the wrinkling. So I went ahead and I spliced this part up. So these are the different layers that you saw. If I go to the ply list, you can see the different plies that I've created. So I have a 45-degree full body, which was spliced into P1A, B, and C. Okay. So we have a small piece here that wraps partway around this very, very deep trough, and then we have a little patch. Ply 2 is the ply that goes along the reinforcing belt area, and here you can see it's smoothing along this curve. That's a mapping of the 0 direction over to this location. That double-headed yellow vector is indicating that it's a 2-curve simulation. Then I have a full 0 degree, which is spliced with an overlap. Then I have a 45-degree, and here you can see the 45-degree direction is here, but I'm smoothing a minus 45-degree bias. And then I have another 45, which I spliced a little bit differently. So if I light up both of these 45-degree plies, you'll see none of the curves overlap themselves. So I've spaced this so that everything is we're not going to have double overlaps on top of each other. And then I have another reinforcing ply and then 2 film adhesives. So if we go look at the simulation results, I've actually run these already for you. And if I just turn on extended simulation, we can see the level of manufacturability. As I said, this had a large area of red here before. When we go to look at the video of this being laid up, you'll see there's a little bit of material distortion that takes place here. The fiber pads you're seeing blue indicate little or no deformation. Where you see yellow, that means we have some deformation, not yet a severe wrinkle or a manufacturing concern. If we were to see red, that means we've exceeded the limit or lock angle of the material. In this case, the material has a included angle on those little diamonds of greater than 30 degrees. And so that indicates that they have to do something to trim the ply down, to change the shape of the ply, add a dart, or splice it. So for this particular design, these 3 plies that you see here are going to be shown a little bit later being manufactured, laid up on the tool, and they laid up without difficulty. Okay. So after we've just designed all these plies, the next step is to go ahead and generate the flat patterns. And that's very easily done. It's simply a click of a button. Fibersim will generate the flat patterns for us. And if I zoom out here, we'll see that flat pattern layout that I created. And once again, as I mentioned, we have associativity to these flat patterns. So if I click on a given ply, the boundary simulation light up and you see the corresponding flat pattern light up. So it's very effective for helping to understand the definition and communicate what's to be manufactured. There's very little ambiguity when you're working with Fibersim. Okay. So popping back over to the PowerPoint, we're going to understand the efficiency of this digital twin that Leigh mentioned, right? We have identified the manufacturing challenges. It enables us to make very intelligent decisions about how to splice and dart the plies so that they can be manufactured easily. The goal being to make this something that's very easy to lay into the tool. As Leigh mentioned, you don't be doing design on the tool. You don't want to have different people interpreting it different, adding excess material or putting darts in different areas. If you hit that layup start point, smooth it the way it was designed in Fibersim, the ply is going to go to the extent of the boundary and lay up without issue. This has been proven for many years. I created a splice group for you just to show you the automated splicing capability, although it was required on this part. You can have different splice groups of different orientations for different ply groups. You can also use more than one splice group on a given group. So if you have a large wing skin or fuselage section, it's something that's being hand laid. If you don't have a ply longer than 8 or 10 feet, if you don't make something too difficult to lay up, you can have multiple splice groups applied to a single layer or group of layers, and they will work effectively. And then we saw this generated all the flat patterns for us. So the last section of the demo here is going to be talking about deliverables and how we consume that digital twin to generate other information. And here we can see a single page of a ply book. So we're going to talk about some of the documentation. We're going to go through laser projection and look at flat pattern export. Before I go into some of the documentation side of Fibersim, I want to point out that we can very easily create a variety of different types of reports or outputs. There's an ability built directly into Fibersim to generate a variety of different types of tables. So we have actions built in. At a click of a button, Fibersim will take the composite hierarchy in Fibersim, and here you can see a CSV table of this definition. We can make CSV or HTML files. Went ahead and made a weight roll-up as well, so we understand the area of each of the flat patterns. We can roll those areas up, and based upon the aerial weight you put in your database for your material, we can calculate your total net part weight. I did not run all the plies for the overcore, so some of the overcore information is incomplete, but for the OML, the weight should be accurate. We can also do cost analysis by using the cost per area that you have defined as well. We go to look at MBD processes and how Fibersim can automate the documentation of the design inside the CAD system. We have a variety of different tools. We have many customers that have been doing this for years. They don't make drawings anymore. They actually do everything with a model-based process. So what we're seeing here is basically a piece of leader text that was defined in NX, and I've taken a design station and I've linked it to a core sample annotation. So Fibersim basically pumps all this information directly into this location, and you can tailor what you show as far as summary information or how many different rows of material, different columns you want here just exposed. I've seen many customers put these on opposite sides of a drop-off area on a ply cross-section. Here we can see a ply callout. So I have a point on the boundary, and by making a leader that emanates from that point, Fibersim will go ahead and put the list of the different ply objects that are using that section of the boundary. And then here you can see a actual ply table, composite ply table. I tried to style these a little differently using different fonts, but basically we use all of the native PMI capabilities in the CAD system. So the color, the size, the fonts, things like that. And then we just write data from Fibersim into that text annotation. Here you can see a place where I've made a planar cross-section. And here you see the planar cross-section for the OML displayed on the surface here. I went ahead and zoomed in a little bit so you can see exactly what's going on, because if I try to put the whole thing on there, it's going to exceed the borders of the screen. But here you can see I've made a shaded cross-section of all the different ply drop-offs in this belt line area. Okay. Once again, all this is automated. If I change something in design, these documents got a date. I just click on the document, it updates based on the current definition. When we go to make a ply book, here you can see P1C going down on the tool. As I mentioned, this is indicating a standard simulation, so someone's contacting the material and working out radially until they touch the boundary. We have an image of the flat pattern, the material name, orientation, page numbers, the laminate number, name. Here we see the last little P1C. Here's the first strip ply, and this is actually Once again, communication of that two-curve simulation. It's a line with little arrows going out either side, showing that you smooth in this long direction and then work out from that. And then we have another full body ply, and then another full body ply splice there. So that's some of the documentation Fibersim can make. For laser projection, we take the boundaries that have been defined for each of the plies in Fibersim in 3D, and we automate the generation of the laser projection file. Here, I've actually imported that file back into Fibersim just so we can display it and look at what the boundary would look like inside the CAD system. So this is what the laser would project. Here you can see the layup start point and the fiber direction curve. So all the same information that's on that ply book can be presented to the laser projection system. And this is P1B. You'll see this ply getting laid up on the video coming up shortly. Here's that same ply. I exported the flat pattern as a DXF file. Fibersim optimizes the shape, so we make the initial flat pattern by unfolding the 3D fiber cells, making them orthogonal again and drawing a spline around the outside. And then we have some technology when we export that to allow you to optimize it and clean up the boundary, put fillets if you'd like on an extended boundary, and to make that more efficient for the cutter to cut. We can also put text labels, as you see here, the name, orientation. There's a variety of different things you could enter here if you'd like. So with that, I think I'm going to go ahead and pop back into the CAD system. I want to make a design station just to show you what that is. That's what's used to go ahead and drive the information into the PMI annotation. We'll then go ahead and just quickly look at the planar cross-section and PMI results. I'll show you the actual PDF drawing sheets. I made a PDF ply book as well, so I'll show you the drawing sheets in the CAD system and then an electronic ply book you could use to put on a tablet or something in manufacturing. And then very quickly, we'll look at the laser projection capabilities and the flat pattern export utility. So back in Fibersim, the first thing I want to do is go ahead and hide these flat patterns. And then I would like to go to Design Station. So a design station is basically a point on the surface. So you can see a point highlighted here in green. And at that location, I'm going to command Fibersim to drill through the definition. So instead of taking a core sample, at that location where this point was selected, it's going to drill through and it's going to tell me what it finds as far as components. So it tells me the exact XYZ location. It says it found 6 components, total thickness of 1.14 millimeters. And then it lists out each one of the different plies that it encountered. So we can see all the different plies that it hit, and it gives me the percentages of those different plies. It's just a summary report. There are different levels of core sampling capability, but I need to do this to update the PMI. That information is going to be pumped into a annotation for the PMI result. So now if I basically turn on my PMI, here you can see the core sample annotation that we just created based upon the design station. If I would like to edit that, I simply come into the core sample annotation. And as I mentioned, if I'd like to change this from summary information, count and thickness, which you see listed, to be just the count, it's instantaneous. If I want to change the component information and display the material as well, it puts that in there. Once again, all of this is staying parametrically linked to the definition. The only necessity is that that core sample be up to date. And then you can use the CAD system to move this around, position it wherever you'd like. Here you can see the table. This updates automatically. You don't have to go and click on that one to update it. You can see that this has gone out of date. So if I simply click on the apply call out and I click update, it just updates that for me. Okay. It's a very, very convenient, very capable way of documenting your part if you don't want to spend time making drawings. The plane of cross-section is something that's created by simply picking a plane on the surface, and then after you define the location you'd like that to be constructed, you simply go ahead and request that Fibersim make a cross-section. And so now it's actually building the cross-section for me. And I think I accidentally had turned on generate construction curves. So one of the things I want to point out is you don't have to build the actual curves. You can just have the cross-section be a display object as I did for the PowerPoint. But what it's doing right now is it's actually building all the different little rectangles for each ply for me. And after I do that, I'll zoom in and show it to you. So the cross-section response time is very, very quick when you don't build the curves. People only build the curves, they want to share them in a drawing or make an illustration. This will be done in just a second. I apologize for accidentally hitting that button. Once this is done, I'll go ahead and show you the laser projection capability and the plybook. We find a number of customers that give us data to do benchmarks and evaluations. They'll oftentimes provide us with drawings. And when they do that, many times we find there are errors in the cross sections that they've made manually. And so that's something that I think is very powerful, is that this cross section being created from the exact definition that's in the model right now. So if I go ahead and zoom in here on this, you can see the actual ply drops. Let me do one thing. I'll turn on the view with edges, and you can see the edges of the plies now. Here you can see where the splice ply took place. See the core definition. I have step 4 defined in here. And we have a splice under the core in this location. Okay. It's actually a very efficient way to document this. A number of people have used this with great results to help document their designs. So I'm going to go ahead and hide that cross section. The next thing we'll do is we'll very quickly look at the plybook. I'm going to simply tab over to the drawing view here, and then for each one of the plies that I've created, this drawing format or template has different text entities here that are linked to Fibersim. So I just have a reference text item, and then Fibersim automates the generation of all these sheets. It puts the shaded image with the layout technique here, as well as the flat pattern. Increments the page numbers for every single one of the plies. It does that in a very quick automated fashion. If you have a change in 3D, you simply come here and update the sheets. And then this can be published to a PDF document as well. So here you can see I've basically taken the sheets that I created. If I just fit this to page, I can actually display all those different pages for you. And you can do this on a viewer or a tablet in manufacturing very easily. The last thing I'd like to show you is the export of flat patterns and the laser projection. So for flat pattern export, we're going to simply go to File, Export, and then come on down to Flat Pattern. And you can see here we can do DXF or IGES, as well as a variety of different nesting systems that we send direct files to that have a PPI file. Go ahead and pick DXF. For this one example, pick the extended ply. You pick a range of plies like export. I just did it for the P1B, the one that I showed you I imported into the PowerPoint. You can specify a variety of different settings here, as I mentioned, to optimize that. Instead of lines, we do lines and arcs to clean up the boundaries for curved shapes. You can have a minimum line length, a length ratio, and if you'd like, a fillet radius. I actually have specified different layers for the cut layer, for any types of markers or legend that goes on there. I mentioned that there are text label capabilities. This isn't part of standard DXF, but we've augmented that. Many of our customers have told us that they spend a lot of time before they use Fibersim going in and taking flat patterns to AutoCADs that put labels on them. So you didn't have a non-shaped and a list you had to try and collate. So you can put all kinds of different text onto that flat pattern. We can export this to a file location, or if you're using Teamcenter, all of the data that's in Fibersim can be published to the Teamcenter. We can publish the entire composite hierarchy and then link the actual plies directly to the Teamcenter items. Okay? So that's a simple button click, and it sends out the DXF file for the flat pattern. And then if I pop up here and go to export and we look at analysis for laser projection, I did the similar thing. I did all the plies, first to last, extended boundary, specified I want a .ply file, and I told it to put the origin and markers on there, and I exported this file once again just to a location. That creates a .ply file, and then if I'd like to import that and verify the laser data, I can simply come down to laser import, and inside here I can display each one of the boundaries that the laser projection system would display on the manufacturing tool. So here you can see, and for the one you've seen a minute in the video, we have these 3 plies, P1, A, B, and C, are going to be laid up in just a second in a short video. So I'm going to return to the document, and we'll look at this real quick video that shows these plies being laid up. So P1A is going to be the larger ply you see in a second. It's a very large one on the right. P1B is that forward one. P1C is in the center. These are the simulation results, and you see that area in yellow. That requires that the technicians smooth that material and work it a little bit. So they're going to have to deform the normally orthogonal fiber cells, but it does go lay into the tool, and it lays out exactly as shown in Fibersim. When they go to lay the next one down, if they were using laser projection, probably a little more accurate, but there should be a half-inch overlap here. There's 2 areas. You can see that in yellow. Those are the 2 areas that probably require the most work to smooth it in. But they were able to put that in relatively accurately as well. And then there's one smaller piece on the inside where we have that very compound curvature. You can't have one ply absorb all that deformation. At least this prepreg wouldn't do it. And so there's the part laid out that you just saw in Fibersim. Those plies went directly to SDA as DXF files, and they went ahead and cut them and laid them up for us. So I think this shows how we can actually save you some time. Fibersim is going to improve the accuracy of the data, the engineering data you create, and the efficiency with which you can transfer that to manufacturing. It's very important that, as Leigh mentioned, you don't have any kind of blockages between the different disciplines. You want to be able to consume that data and make the part very accurately. The documentation is all generated automatically, and then it's all updated when changes are required. So the big point here is that we offer this digital twin or digital thread and make sure that that's going to be accurately, easily consumed. One last slide that shows just some of the other benefits customers told us. One of the big ones is the 60% faster layup, because these flat patterns have been evaluated for manufacturability based on the material form and shape. They lay up very quickly, help you to reduce costs, save time, and basically improve your profitability rate and quality. Thank you.